Okay, I'm going to run through this real quick. Your board, Mark, KF6WTN is your repeater and technical and site chair. Keith, KM6CSW is your scope editor. John, WB6IQS is one of your directors. Kevin, AK6FRK is your other director, back there in the back. Glenn, who you heard from earlier, AI6RR is your membership chair. Tom, W0NI, also in the back there, is your treasurer. Sandy, KK6EED, diligently taking notes here in the middle, is your secretary. Michael, KB6D, back there in the back, is your vice president. And I am Joe, K6JPE, your president. With that, I will turn it over to Bob, AK6R, talking about the ABCs of RFI.
Hello, there we go. You really got to get into this mic, don't you? Yeah, all right. Well, good evening, everybody. I recognize most of you here. I know there's a few people who've seen or heard this talk before. I gave it to the DX Club. I did it by Celia, and I also will be at HANCOM in 2017 up here in Torrance. And this presentation, by the way, is already on our website. All the PowerPoints are up there. You can also download it in PDF form. So, anybody know what RFI is? Ever experienced RFI? Oh, yes. Oh, yes. Well, what we're going to do tonight is we're going to solve two problems. One is, are you the source of RFI? All right? This is your neighbor who's knocking on the door. That's my ex-wife on a good day. Notice the finger. It's all that fault. So a lot of us are the source of RFI. We cause lots of problems, okay? You ever heard your wife come in during Dancing with the Stars and say, honey, you got to turn off the radio? It's happened.
Leave your words out.
I know. The other aspect is, are you the victim of RFI? And more we are the victims of RFI from all these electronic devices that are in our house, in our neighbors' houses, solar systems, you name it. Right? They're all over the place, and we have the symptom. We notice it because there's a symptom of a high noise floor. All right. So, what I want to do tonight is the objectives would be very simply to learn the fundamentals of RFI. In other words, how to identify it, what are the symptoms, how do you pinpoint the causes, and some simple cures. We're going to be specifically talking about ferrites and how to choose and buy the right ferrite for your particular issue, whether it be a source or a victim problem, and how to use ferrites to solve the number one problem that's basically shared by all hands. We get about 30 calls a day from everything from sprinkler RFI to garage doors opening up over Air Force bases. You know, it goes on and on and on. And we even got a call, and some of our products are on the International Space Station. So RFI is everywhere. And we want to know how to use the ferrites to solve both RFI transmitter problems and receiver noise. So the first thing I want to do is teach you a little bit about ferrites. What are they, how do they work, and all those types of things. So it's time to put your thinking cap on, and we're going to do RFI 101. All right? A lot of people know about ferrites, but some don't. And so this presentation has basically been put together for all different types of ham radio operators. Contesters, DXers, rag chewers, old-timers, beginner students. So the first thing we want to talk about is what is RFI. It stands for radio frequency interference. And Palomar Engineers does everything from about 100 kilohertz to 2 gigahertz. So that's kind of our wheelhouse. We don't do anything above that or below it. But basically, the definition of RFI, it's a radio frequency disturbance that causes an unwanted interruption, degradation, or unintended operation to an electrical circuit. That sounds like an MIT definition, doesn't it? All right. But the common sources that for RFI, and particularly if you've been on 40 meters or 80 meters lately, the sunspots have been driving everybody nuts because the noise level is high. You can't hear the guy next door, but you can hear a guy in New York, for example. Okay. So there are natural RFI sources, including the sun, cosmic noise, lightning, atmospheric static. And those types of sources, there's not much you can do about them except grin and bear it. Right? So the things that we're going to be talking about tonight are how do we solve man-made for RFI. And that can come from several different things. One is radio transmitters, amateur broadcast, consumer devices. Most of you don't think that some of your devices in the house, like a UVerse system, can put out RFI. But I will tell you, every 23 kcs, the UVerse system is saturating your house with RFI. All right? It's a real problem for a lot of people, depending upon what you have in the house. Motors, ignition systems, power lines, anything that's a square wave generator will cause a problem, including wall warts. And in California, there's a new law that basically says everything has got to be, for all the new motors, they have to be pulse width controlled. All right? So in effect, they have to be energy saving. And what that means is they end up being pulse width modulated. And we've seen a lot of air conditioning units and heaters that have come in with PCMs in it, and it just drives you nuts with noise. So from a transmitting standpoint, there's of course one thing that always goes wrong, and that's the wipe alarm goes off. And when that goes off, you will hear it. From a receiving standpoint, there's lots of sources outside your shack that cause problems, primarily neighborhood, the other devices in your house. And the symptom that you'll hear is birdies, chirps, buzzes, clicks, broadband noise, distorted receiver audio. You don't know where it's coming from, but the symptom is a high noise level. It might be S6 or S7 or S9 or 10 over, all right? So we're going to talk about those. Anybody have any of those problems at all? You got high noise levels? When you transmit, does your subwoofer go off in your home theater system? All right? That's a very, very common thing to happen, all right? I moved into a new house and I had sprinkler RFI for about 2 weeks until I figured out finally where it was. Every time I was on 80 meters, the sprinklers would go on. My wife would come running out saying, "Hey, your sprinklers are on." So finally we solved that problem. And, we'll show you how we did it. But garage doors opening and closing is a real common thing too, right? As well as Christmas tree lights, and it goes on and on and on. Okay, so one of the things we have to know, and you have to know when you're troubleshooting RFI, is how do you get RFI? And RFI is a pretty straightforward concept, but you have to have three things. You have to have a source, you have to have a path, and you have to have a victim. If you don't have any of those, all right, or you don't have any one of those, you don't have RFI. If you have no path between the source and the victim, well, there is no victim, right? On the other hand, most of the time when you have a path, the hardest thing to do in RFI is figuring out the path, all right? How are you getting interference to your particular situation? And there's 4 different ways that that path can take place. It might be radiation. Your antenna is right above your TV set, for example. You're in the near field, you're just saturating that, and your TV goes bonkers, all right? Or your home theater system, whatever it happens to be. Or you transmit and your computer shuts off. That's hooked to the radio, right? It happens all the time. And that's purely caused by radiation, but it can also be conductive, all right? I've seen stepper motors where the control cables don't have chokes on them, and that when you energize them, it feeds back into the radio system and it locks up some of the radios and stuff, all right? That's another one. I mean, it goes on and on and on, but another way is inductive or capacitive. You got your feed line, it's coming across the top of the roof, it's right in the attic, right above your AC line, and guess what? We get some inductive in there, and on 80 meters, you're coming through the subwoofer. Okay? Same thing. Capacitive is the same thing. And the interesting thing about paths is it's usually multiple paths, not just one. All right? It reminds me of that old whack-a-mole game where you hit the mole and another one pops up. What happens is the same here. If you put a stop sign for the conductive RFI, old Eddie Electron who wants to go to ground, that's what he wants to do. He's going to find a different path. And we'll go through some examples of how to identify the paths and stuff. Okay. Well, in order to have a path, all right, of electromagnetic wave, you need some type of receiving antenna, all right? And here's typical antennas, and they're very much dependent upon the frequency. So on 160 meters, how long are the dipoles? They're really long, aren't they? 270 feet or something like that, right? So when you're transmitting on 160, 80, 40, 30, pretty much, antennas that will pick up your signal tend to be long, all right? And so what's the longest antenna in your house besides your transmitting antenna? Typically it's the AC lines. It could be long Cat5 lines. It could be telephone lines. That's why telephone RFI used to be a real problem when we all had landlines. Now we have cell phones, that problem has pretty much gone away. If you're living next to KFI, I have lots of customers who live next to KFI, and their microwaves will go off, their garage doors will open up, and that type of thing. But usually the solution is to choke the AC cables coming into the defective device. It stops it, and you don't have that type of problem, because the antenna is the AC again, all right? However, on the other hand, if you are transmitting on 20 through 6 meters, okay, usually it only takes a short antenna to pick up the signal that causes a problem. I'll give you an example. I was transmitting, I got the 6 meter bug a couple of years ago. And so I have all my radios go through a PA system, and then the PA system goes to, binaural stereo and all that kind of stuff. And so I started transmitting on 6 meters, and all I got was garble coming out of the speakers. What was happening is my speaker wires happened to be a half wavelength on 6 meters, which isn't very long. It's like 9 feet, right? And so the signal was being picked up by the speaker wires, put back into the amplifier, garbled, and then it was being shot out again. And the symptom I heard was garbled, okay? We put some chokes on the speaker wires next to the amplifier, solved the problem altogether, okay? And believe me, I have lots of chokes in my shack. But here was one that snuck through, just because of the length of that particular wire, all right? The antennas, they pick up the radiation, okay, if you remember your hand test, there's a wave going through the air, and it induces a current in a piece of wire, all right? And that wire is called, it picks that up. And typically it's called common mode current. It's induced in all the conductors on a particular cable. You got a cable, 6 wires in, they all get current on them, all right? And so the challenge is how do we stop or reduce that current so that it doesn't affect the devices that we have. Basically, the way you can reduce the current is you have to choke off the antenna. So on the left-hand side, we have a typical radiation. That might be your transmitter. And it's transmitting out, and you're 50 feet from your neighbor, and your neighbor's got their AC power lines, of course, running through all the house. It picks up the current that's induced in that, and then it goes in and it bothers their device. But if we put a choke or a filter right next to their device, or even yours, it will cut off effectively that current going into the device, and therefore you won't have any interference on it. All right, so what we're going to be talking about tonight is where do you get those chokes, how do you put them on, that type of thing. On the other hand, on the right-hand side, your transmitter may be the source, and it's transmitting up to an antenna, and it's also maybe putting some of that power. When you have a transceiver or an amplifier or whatever, all the power does not go up the coax. Right? It's going to tell you that. Some of it actually goes out through the AC lines. Very small amount. Some of it may go out through the interconnect wires. All right? But it all doesn't go out the coax. And so what happens is you're sitting there and you have a nice new 5 kW amplifier or something like that, or 1500 actually, 1500 watts, 2 RP. And so what happens is a lot of that power, most of it goes out the coax, but some of it may not. It may go to ground through a ground loop or something like that, and that might be such and such length, and that causes interference. Well, the solution to that, of course, is every wire that's going in and out of your transmitter should have some type of choke on it, so it stops it. That doesn't happen, all right? Except the antenna, but including the antenna. And I'll tell you why in a second. The cable, the coax should have one. But for a different reason than you're probably thinking. Okay, so we're going to talk about how do we create those chokes and where do we put them. And we're going to be talking specifically about ferrites because there's multiple ways to create these chokes. Some of those are resonant traps, ferrites, low-pass, high-pass filters, or specific band-pass filters and things. But it's much easier I think, to use ferrites to do this because they're broadbanded, they work over a larger frequency than just a specific tuned choke. All right, ferrites come basically in 3 different sizes. One is 3 different shapes. We call them topologies, but they're actually just shapes. There's a slip-on bead, kind of like a ring you put on your finger. There's snap-on beads, which snap open and you can put a wire in the middle. And then there are rings, right? Those are the 3 basic topologies. They're not ferrets, F-E-R-R-E-T. I had a lot of questions. Well, where's the ferret? It's not a ferret. Ferret, right? All right. Well, the characteristics are simple. They're easy to install. They suppress RFI from 100 kilohertz to 2 gigahertz. Really simply, they can be put on just about by anybody who understands what's going on. They work on all the conductive paths, and the antenna feed line, AC, DC, and I/O cables are what most of us worry about, because that's where it's going to either get in or it's going to escape from what you're doing. There's lots of options and sizes and shapes to suppress most of the paths. The rings, for example, all the way down from 1/8 of an inch wide up to 6 inches wide in the inside diameter. So depending upon whether you have plugs on them and all that type of thing, you can get different sizes to do different things. And they're very effective, but you have to understand 2 things. How do you choose the right ferrite for the job, okay? And where do you install it for a particular problem, right? So it will be different that if you're a source versus a victim, right? As a source, you've got to solve the victim's problem. As a victim, you've got to solve your problem to stop it coming into your radio room, okay? So in order to understand that, you have to know how ferrites work. And we're going to spend a couple seconds here on how ferrites work. Ferrites, if you think about it, in simplified terms, ferrite beads are basically frequency-sensitive resistors. All right, real easy way to think about it. All right, and they have a impedance that's a function of frequency. And in this case, we have a ferrite. It's impedance on the y-axis and frequency on the x-axis, and you'll see there's a big peak there, very similar to what you'd see with the tuned circuit. All right. In the middle peak, there's actually 3 peaks. There's a red one, and a blue one, and a green one. And the goal of using ferrites is to operate it so that it's between the 2 blue lines there, where it's resistive. All right? And the reason that we're going to do that is because the resistance will dissipate the common mode current. All right? So the bead must be used in the resistive region to act, so it acts like a resistor. It's got lots of capacitance. Capacitance doesn't dissipate energy, right? It leaves it or lags it. So how can the resistance be increased? So we have a ferrite, all right? It's a variable resistor, and the question is how can we increase its resistance? Why do we want to do that? First of all, remember Ohm's law, E, I, R. So what does I equal? I equals voltage divided by resistance. You make a bigger resistance, guess the current goes up or down? It goes down, right? So the goal is we want as big a resistance as possible in our circuits so that we have less and less current either going into the victim or being transmitted out of our transmitter. Right? It will not affect the signal inside a cable, but it will affect the common mode on the outside of the cable. We'll show how that works in a second. So, by the way, I forgot to mention that I'm going to be giving some prizes away at the end of the lecture. I'm going to give all the answers out. I just won't tell you what the questions are. All right? So you have to listen up and be careful. When I emphasize something 3 or 4 times, it's probably a good clue that that might be one of the questions. All right? So far, we haven't gotten any of the answers that you need to be able to answer. So, but listen up. Listen up. Pay attention. All right? How can resistance be increased? All right? There's 2 basic concepts here. One concept is ferrite resistors add in series. It's like regular resistors. You put more in a row, you get a higher resistance. So here's an example. All right, you've got 3 chokes here. One's with 5 beads, one's with 10 beads, and one's with 15 beads. This is the 5 bead impedance. This is the 10, and there's the 15. So at low frequencies, you'll see by putting more beads in there, it actually increases it until you get up to about 30 megahertz, and then at that point, it doesn't really make any difference. all right? So if somebody tells you, well, put more beads on at 6 meters, that you're just wasting your money because all you need is 3, all right? You shouldn't put 15 on there. There's no need for it. Well, in this case, for these types of chokes, they all tend to converge around 10 meters. So for a beam or something like that, five beads is fine, all right? And I'll tell you how to measure and determine how many beads you need depending upon frequency in a second. In order to, from this point on, we're going to use impedance rather than resistance because impedance is a little bit easier to measure on meters and stuff. So impedance, which we have on here as Z, is equal to resistance plus or minus the reactance. So generally, a higher impedance given small reactance will be a better characteristic. So let's go on to the next slide. So the first way is you put them in series, all right? The second way is you put multiple turns through the ferrite. But here we get some magic, all right? The magic is the impedance increases as the square of the number of turns, all right? So there's an example here. So if 1 turn is equal to impedance Z, whatever Z happens to be, that's a function of the ferrite and a bunch of other things. 2 turns will be 4 times that. 3 turns will be 9 times that, all right? So an example on the bottom there is you have a 1 turn, it's 1 turn, every time the wire goes through a ferrite, it's a turn. So this is just a simple 1 turn ferrite. This is a 3 turn ferrite, and this is 7 turns, all right? So the 7 is going to have a much higher impedance than the 3, which is going to have a much higher impedance than the 1. All right? Or you just use it for radials. You don't really need to put it to a ground rod. But in order to get isolation and choking, you need to isolate this ground here in the coax from this ground here. Otherwise, you're just shorting out that particular part of it. You've got 2 grounds and you really don't have any effect at all. Right? When you're putting up a vertical, this is a typical way you would do it, or an end-fed antenna. End-fed antennas tend to have impedance transformers built into them, and they may also need chokes, but we'll show you how that works in a minute. Unknown number 2 comes in all different sizes and shapes, and they're all called many, many different types of things. Basically, coax in, coax out. So the ones that I showed you here, these are all unknown. And they're all different topologies or different shapes on them, and they perform different things. They perform different resistances. And so they'll come in boxes, tubes, snap-ons, and we even have something called a super choker. For the boys with the big toys, they need a super choker. It'll do 10 kW. That's a lot of headroom. We just call it headroom. On the other hand, balance, okay, you usually have balanced output. So here's one, for example, for a dipole. You would hook the ring here, here's another ring to hook the wire to, and this is a hoist it up, and then you have the wires going to the 2 outputs, which are identical. You can also have just 2 outputs up here, or you can put 2 outputs on the side. Lots of different ways to do it, but the idea is, here's an example of one. This is a 4-to-1. It's got a 4-to-1 impedance transformer and a choke. We're the only guys that do that. And so this would be used for a dipole. You hoist it up, and this is actually used for an off-center fed antenna. You're feeding it off the center, not in the middle. And by doing that, you can get multiple bands. And so this is an example of a balun, okay? This is an example of a balun. It's just got different connectors on it, okay? What's inside the box is identical. It's just either wider or bigger or higher powered or whatever, but basically what's inside the box is the same. And this is a typical unknown. Right? It's got coax on each side. It's the same as these over here. But this has got 15,000 ohms of choking, all right? And there's specifically a reason to do that. And then these have 500 ohms, all right? And if you get down low enough in frequency, you need to put 10 or 15 of those on to get that 500 ohms because it's a variable resistance. Okay, where's my little clicker here? All right. All right, this is the one we talked about, the ugly balun, ugly unknown. All right? These work great on 1 band, or maybe 2 bands. If you cut it for 15, yeah, you'll maybe get down to 20, it'll maybe get down to up to 10, all right? They're basically tuned circuits. You have an inductance, and you have about 25 picofarads per foot, all right? And you have a parallel circuit, A parallel circuit has a high impedance that you're trying to put through it. So what I did on this one, and I'll pass this one around right now, is I actually did the graph on the side of the unknown, so you can see how narrow it is. All right, and you know, just start passing that around, and I'll pass another one around over here. This is identical. This just happens to be a small coax, and this is 40 meters also. Useless on 80, useless on 20. All right, there's essentially no impedance at those frequencies, or it's so low that it's not useful. All right, so those types of unknowns are useful for single bands generally. What a ferrite does, instead of being a very peaky impedance, the ferrite will broaden that impedance out like this, so you can use it over multiple frequencies, 10 to 40, 160, 80 through 10, those types of things. All right, and we'll see how that works in a minute. This one here, just to recap it, about 3,000 ohms. It's got 20 feet of coax in it, and it's only effective for 1 or 2 bands. All right, and you can see what the curves are. Every one of our products we put on the websites have the impedance curves with them. All right, we've got one in a tube that's good from 1 to 160 megahertz, and it's above 5,000 ohms across the whole bit for the whole range. All right, a little proprietary design, but you know, it took us a while to get it, but it works really well. But you know, it'll only take about 1,500 watts. You want to put the amount of power that goes through these ballads, by the way, is not a function of the ballad or the unknown. It's a function of the cable size and how big it is to put that much current through it. So you can put whatever the limitation on RG213 is, which is probably around 10,000, 15,000 watts on 80 meters. All right. Of course, you'd never run that much, but they'll take a lot of power. By the way, you can use RG6, the satellite coax. It's really cheap. It's like $50 for 500 feet at Home Depot. That'll take 1,500 watts on 80 meters pretty easily, particularly if you're just running PEP. And it's cheap. Works really well. They make good chokes too. Okay, feed line chokes. Again, we talked about these. These are the little small ones. I'll pass those around. Same thing. You can either buy these as kits and with the shrink wrap and stuff, and put your own connectors on them, or you can just buy them pre-built, and you choose a number of beats depending upon the frequencies that you're going to use. The 5-beat one will basically work from 80 meters up if you don't have a lot of current. You don't have a lot of common mode current. If you do, then you need to get the larger ones. Okay, other types, we have the snap-on beads here, all right? And you'll see there's 5 beads there, about 500 ohms, 150 to 500 depending upon the frequency. And then the last one is just a bigger snap-on. But it shows the principle. Here's 3 of them in series. They're each about 1,000 ohms because you can only put 3 turns through them. And each time you do that, it's about 1,000 ohms total for these. So if you put 3 of them in series, you get about 3,000 ohms. Right? That's pretty good. I was running a big 80-meter loop with these 3 in series, and it works just fine. Right? And I was pushing it power-wise, so you needed something that would take the power too. Super chokers, same principle, but you have multiple ferrites for higher power and a different frequency range. And so with these, you can see it's a lot broader than it would be with just like an ugly balun, which would essentially go up and down. So this will cover 80, 40, 20, 15, almost all the way out to 10, past 10 meters, and you still have 500 ohms. All right? And how do you determine what that's going to be? It's the number of turns in the mix. All right? So some of our sophisticated ones have multiple mixes and different turns on them for different purposes. That's how you broadband them out. Right. Our most popular one is the one we have for 160 to 30 meters, and that one's got choking impedance over 10,000 ohms. Really a nice one. Got 7 turns of coax for it. This one here, I told you before, this one here has got over about 5,000 ohms over a huge frequency range, 1 to 161 megahertz. You could use this one for anything. Right? And in some cases, you're going to want to use them with little grounds on them because you may have long feed lines. If you're in a contest situation, you got the coax going everywhere, All right. What happens is the coax inductively couple to each other. So you're working guys on 20 meters, and it couples into the 40 meter guys, which couples into the 80. And it's only because of proximity. And it's common mode current is what it is. So what you do is you put line isolators in there and you take them to ground periodically at a certain, half wavelength, and that kills that common mode current. Right? And so that makes operating a lot easier. But we came up with this one because it's really broadband and you can use it for all different types of frequencies. Again, they come in boxes, and the boxes essentially have either beads in them or they have a large toroid or ring with multiple turns around here. By varying the number of turns and the mixes, you can change what the frequency is. That's essentially how those work. These are great for inline chokes, beams, dipoles, loops. Anything that you can hook coax to, these work just great. Here's an example of an end-fed choke, how they're used, right? And we're going to show you in a second how to actually make one. Here's one of the products that we make. It's called a bullet antenna. It's shaped kind of like a bullet. It's a impedance transformer down here. It's actually 9-to-1. And this is a 55-footer. It's going up 18 feet, going over here. And whenever you use an end-fed antenna, the coax is part of the antenna. You want the coax to radiate. Right, so you wouldn't want to put a choke right here. You want to put a choke down here right before it gets in the radio, or at least outside the shack, right? So that you're using this as part of the radiation. And this little guy, if it's 55 feet, it'll do 80 through 6 meters fairly easily, virtually without a tuner. The SWR is typically less than 3-to-1, right? Or if you have a tuner in your radio, you just hit the button and you've got one antenna for all those different frequencies. Yeah.
I keep seeing you wrap the coax in fairly tight loose. What effect does that have on the 3D feeds? I was always taught that's a bad idea. Getting it too tight.
Well, it becomes an issue if you are using a cable with foam inside. We don't do that. We use Teflon for everything. And so it doesn't migrate. Right, so the problem that you run into those types of things, particularly, and that's an RG6 problem too with the satellite cable. It's got foam in it for the most part, for most of you, and it will migrate as it heats up, and it will short out to the outside braid. So you don't want the turns too small. On the other hand, our super chokers have 1 foot loops in them, right?
So you want a handle on it.
Yeah.
Don't have something to sit on.
Looks like it. Well, here's what it looks like in principle. For $10, you can make your own. All right, you have your own coax, and you put on there anywhere from 8 to 12 turns, depending upon where you want the peak to be. All right, you put 6 turns on it if you want it to be in, let's say, the tri-bander size or frequency range, or you put 12 turns on it if you're running 160 and 80. And by tuning it like that, that's all you need for a low power. Right? Now, if you want to run bigger cable, that's where the issues start to come up, all right? Because you can put 7 turns through one of these. That one's 2.4 inches wide and 1.4 inches inside diameter. You can put 7 turns of RG213 on that without a connector, all right? That's the principle behind our super chokers. We have to make those without connectors on them, but they have 12 to 15,000 ohms of choke loop, and they'll take whatever the power of the cable is, which is 5,000 to 10,000 watts. For most boys with their toys, that's enough. Although I do get a call from a lot of CBers running inches 5/8 heliacs, running 3x25s or 3x30, 3CX 2500 for 30,000. They're running 40, 50,000 watts. And we solved the problem a little bit differently with those. Because you can't turn helix like that. It's too big to do it. So you have to use quarter wavelength balance, that kind of thing, to solve that problem. All right. Now don't forget, we've just been talking about the coax here, but you also have to worry about your AC/DC lines. Okay, and we're going to go about another 15 minutes here, so if you need to leave, that's okay too. But the RFI also gets out through your AC and DC lines. And you can use the choking principle is exactly the same as it is with coax. No difference. It's just a different frequency. And in the case of AC lines, typically 3 to 8 turns is plenty for the AC aspect of it. So here's just some examples of how that works. So to recap the transmission thing, and you've probably seen this before because it's the exact same principle we've been talking about with ferrites. Determine the frequency range in the path, choose the mix, choose the topology, install the ferrites, retest. And if you get lost, give us a call, and we'll try and point you in the right direction, at least to the right mix or the right, or where to guess where the path is. We've been through so many of the same things over and over and over again. And when the colonel called me from Oklahoma and said we just changed our frequencies, and every time we fly across the new homeowners division down here, we have 100 garage doors built up. Right? Well, I sold them 100 kits, and it solved this problem. But those are real typical things that happen all the time. Receiver RFI. I'm just going to go back one. The principle behind this is less noise equals higher signal to noise ratio. It means you could hear somebody that you couldn't if you didn't have the noise. All right, real simple principle. There are lots of sources of noise that you see as a victim of RFI. One of those is plasma TVs. Some of the plasma TVs are so bad you can't even turn your radio on. Some of the earlier ones. UVer systems, cable boxes, HVACs, particularly those that have been installed recently both with modulation on them. Most of the LEDs now don't vary the voltage, they vary the duration, by the way. So for all the Christmas tree lights and those fancy things that flood your house with all those stars and stuff, we sell a lot of ferrites during Christmas time because they're notoriously bad. People buy them on eBay. There's no FCC compliance. They get them shipped over here, and they're just noise generators. They're just terrible. If you live next to one of those, I wouldn't blame you if the power failed to some of those things. LED lights. I think who was it? Ken had the LED lights on his kitchen cabinet. All right. And your wife says, "Hey, honey, wouldn't it be nice to put LEDs underneath the kitchen cabinets?" Yeah. All right. They're noise generators quite a few times. And conversely, they pick up signals very well. Right. So you'll be on the radio, and your lights are all blinking in the kitchen. You can't figure out why because it's the LEDs. They're coming in through the AC power line. Battery chargers, fluorescent lights, fish tank heaters. Fish tank heaters are notorious. Exercise equipment, computer hash, solar system inverters. There's a whole industry on RFI for solar systems, which we do too. What are some of the other things? Wall warts, those types of things. The path is typically through the antenna coax braid, AC/DC power lines, phone DSL lines, computer to radio interconnect. Same drill, you're just on the other side of the equation. All right? You're the victim now. And you got to think, okay, where is that secret transmitter out here? It's not a ham, usually. Right? Well, I'll tell you a funny story about the ham one. There's two CBers going to go to the motor park. And one guy's got a huge antenna, and he's transmitting 5 or 6 kW all the time. And he uses big guy. This little guy over here, a little bitty antenna, right? And the gal knocks on his door and says, "Hey, you're bothering my TV." He said, "No, I'm not even working. I've been on vacation. It's that little guy over there." So he was placing the blame on that guy, and so he ended up having to leave. But the real problem was still there. Happens all the time. All right, so the path again is usually the same things that we talked about as for transmitting. The victim is usually a radio receiver, and the symptom is a high noise level, or chirping, or furries, or something like that. The solution, again, same thing: eliminate the source, choke the path, protect the victim. One of the things I didn't talk about on transmitting is my wife has a touch lamp. How many people have had touch lamp problems? Oh boy, they're all over the place, right? I don't know why, I can't say women like touch lamps, but they do, and they work pretty cool. But I tell you, they always pick up RF. And the only solution, well, there's two solutions. The first solution is you take a bucket of water and you put the touch lamp in it and don't take it out. The second solution is...
Unplug it first.
Yeah, you unplug it first. The second solution is you actually have, in most cases, they can ferrite the heck out of those things. It's the capacitive touch that's causing the problem. You got to put an RF choke in the lead to the capacitive touch, and that will actually stop it. But you got to take it apart and do a lot of that stuff. So really, the bucket's the cheaper way to do it. Buy her a different lamp. Okay. One of the best kept secrets in ham radio, which has been used for years, but most people don't know about it, is putting a choke at the radio end. Okay, now I'm going to tell you why. All right? Remember, we put a choke at the antenna to keep the dipole from becoming a tripole, right? But from that choke, all the way back to your radio, guess what the outside braid is acting like? A receiver. It's another receiver, because you choked it up here. It doesn't attach to the record antenna. It's a vertical, it's another vertical you got sitting out there, because it's picking up common mode noise from all the people in the neighborhood, feeding it right into your radio. So what do? It's the same principle. You get rid of your neighbors. I'll show you that in a second in a little cartoon. But the idea is you put a high impedance, lots of resistance in a choke that's at the radio. We call them common mode noise filters because the principle is easy to understand. But they're exactly the same thing as we're putting at the feed point. They're just much higher impedance. And they're more broadband, so that you can have one choke that works all the way across the ham bands. You don't have to have certain ones for certain frequencies. And by the way, if you're running multiple antennas, you're running 6 meters, 160, and beams, and steppers, and all that kind of stuff, typically the chokes that you're using are tuned to those frequencies. So a 6-meter choke will be different than a specific choke for your tri-band, which will be different than a 160, for example. So you have multiple chokes that are tuned for those frequencies coming in. Right? Or you can have a broadband one coming in that's on an antenna selector, and it's on the common mode side, the common side, and then just select it, have everything go through it. Not nearly as good, but they do work. So the coax noise filter, in this case, you'll see that they're very high impedance across a big, long range. And here's what it does. In most cases, you'll see 1 to 2 S units of noise go down. All right, if you're in a noisy area, right, you've got lots of people around you, you're in a neighborhood, a HOA or something like that, you've got a lot of noise, you'll see, in some cases, I've seen in some cases in a motorhome park go down 4 S units. The guy can actually transmit and hear now, whereas before he always had a 10 over S9. And he went down to like an S5 and he was, it's thank you, thank you, thank you. And we did it in that case with 2 toroids for $20. And I said, I'll give you your money back if it doesn't work. And he never came back. He told me about the story. He said, Jim, there's 4 S units. There's 4 S units down. I could actually work my little TX 480 we used at the time. And all I had was a hustler on top of this motor. But it was so noisy that it didn't work. So the concept of a coax noise filter is important. And where do you put this stuff? If you have a dipole, you're going to have possibly an impedance transformer. Sometimes you do, sometimes you don't. This is where your feed line choke goes. But between this point all the way back to your radio, that outside braid acts as a receiving antenna and dumps noise into here from the neighborhood. So you can get rid of that in a couple ways. One is you put a line isolator here, particularly if you have a really long run, like a couple hundred feet. You want to break it up a little bit, at least every half the wavelength with one of these, take it to ground. And then right next to the radio, the transceiver, whatever, you put a noise filter, a high impedance noise filter. So it stops whatever is coming, in this case, between here and there. The more you chop this up with line isolators, which are the same as chokes, really, the less noise is going to be coming through a shorter line. Okay, so that's a typical dipole system. A vertical is a very similar impedance transformer. In the case of verticals, usually impedance is less than 50 ohms, like 25 ohms or something like that. So you have to go with like a 1 to 2, 50 ohms to 22 ohms, for example. But there's always a feed line choke on the other end of that. Again, line isolator, back to a noise filter, and then back to your radio. Right? That's a very effective way. It's very inexpensive to do it, but you want high impedance. You don't want to use 500 ohms. You want to use 5,000 ohms or 15,000 ohms. So when the guys on the East Coast were using those big verticals in 160, they got chokes that did almost 20,000 ohms. And the noise level just went away. Right? You're a victim, same problem with AC-DC lines, and that includes get a switching power supply. Right? It's got 2 lines on it, usually a DC and AC. It's a transmitter, but it's transmitting not only the DC through, it's transmitting out to the AC. You got to put chokes on both sides, not just the DC side. If you have a long cable, like 12 feet or something like that, or 10 feet or whatever, between your power supply and your radio, where do you put the choke? You're near the radio, because that's going to choke off anything that's being in between the power supply and that. You may also have to put it right next to the power supply if it's acting as a big transmitting antenna. Right? So again, you got to think about how it would work. We have a wall-worked RFI kit. Basically, this is a mix 77 or 75 right here, because that's the frequency of the wall works. They're typically low, really low frequency, but they're noise generators. Again, square waves, which is the sum of multiple sine waves. You get all kinds of harmonics and that type of stuff. And generally, if you put it on the DC side, you're okay. But in some cases, you got 5 or 6 of them on a wall strip or something like that. You need to put a big ring on the common part that's plugged into the wall, and then that will solve that problem. But they transmit both ways. All right? Eddie doesn't give up, I'll tell you. All right, solar system, same concept. Right now, you got solar arrays, and they all have power optimizers on them, or they got microcontrollers, and some of them even have internet built into each one of them, so you can monitor it. It gets real fancy, but think about all those packets going back and forth, and guess what? Most of the times these are put in what they call strings, which are big loop antennas. And those loop antennas transmit very, very well at low frequencies, and those low frequencies are broadband noise that just wipe out everything from 1.8 to 14 megahertz, which is really, really broadband. You're running field day, we have generator RFI kits, you got long generator lines, 100 feet long, that's a problem. They'll give you lots of RFI too. But you can use the same principles here with collapsed noise filters and feed line chokes too. Mobile RFI kits, same thing. In this case, we have, this is an ICOM 706, this is hooked to, I think it's that one over there, sitting on the table, this for sale. And, but here's the DC line going through a choke. And here's the coax going through a choke. Why do we do the coax going through the choke? Well, when you transmit on some of these mobile transceivers, your instrument panel may go out. Or vice versa. Your instrument panel may be injecting noise into the radio, all right? Or when you run your coax back to the back of the truck or whatever, it's right along where all the instrumentation wire is. As soon as you hit that transmit button, and everything goes. And it goes both ways. So the solution, same as before, on the coax and the DC, and it will cut that out. It'll suppress it a lot. So again, receiver RFI noise strategy, same thing. Assess the source of the path of the victim, protect the victim, which is your receiver, by putting the filters on there and eliminate the source. Okay, we're just about done, and we got one more topic to talk. And that's our friend, my ex-wife. Keep your neighbors happy or you'll get the finger. No, that's not like my ex-wife. She was actually cute in that. By a lot. This is your neighbor's RFI strategy. All right? They're just going to choke you. If I choke you, all right, you're going to solve their problem. However, the hand strategy is a little bit different. And I'm going to tell you a philosophy here that you don't want to fall into, a little trap you don't want to fall into. The hand solution, again, same type of thing. You find the source, the path and the victim. But you clean up your transmitter and your amplifiers first. Make sure that's done. Okay? Now you have to assess what's the neighbor's problem. And I'll tell you, there's several common problems. Garage door openers, subwoofers, and home theater systems are the majority of the problems because they hear the symptom. They can actually hear something, or they in this day, you don't really see video problems, but you may see a video freeze. You see all those little dots on the TV, and some of that's caused because of the overpowering. You have to determine what the faulty device is, and it may not be you that's causing the problem. It may be something else in your house, right? It may be their microwave is interacting with a Uber system or something like that because it's not very well shielded, Right? On the other hand, I've seen where the transmitter goes off and the microwave starts to beep. Right? Beep, 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 beep. And the solution was simple. Take the microwave out, put a filter on it, plug it back in, and then solve the problem. Right? So you have to determine what the problem is and whether it's something in their house or whether it's actually you. Try and figure out what the path is. In the majority of cases, these types of problems occur on low frequencies, 80, 160, and 40, and it's always getting into their AC line. All right? So always start there. It's like if you own a boat, most of the time it's dirty diesel. Right? That's 80% of the problem with the boat is fuel. Right? Here it's the same thing. The concept is the same. Check the AC lines. Something's getting into their AC lines and it's causing it. So the solution is to choke those. But I don't want you to go over and do it for them unless you know them really well. Because you will be doing everything for them that they think is caused by that big antenna. So, what we came up with is a philosophy. All right? We have kits for alarm systems, and home theaters, laptops, desktops, garage doors, miscellaneous stuff, okay? General generic kits. Recommendation is either have them buy, or in some cases you buy, depending upon the relationship is, or have the neighbor purchase it and have them install it themselves. I mean, there's really good manuals with it, lots of pictures and stuff, and like I say, this is not rocket science. It's basically follow the picture, put it on, and then cure the problem. Most problems are caused by AC power lines, and that would generally long wires. Okay. Prize time. I've got 4 questions, 5 questions. And we got some wall wart filters and some rings, and we're going to give those away to somebody, the first person that knows the answer to the question. What's the first question? All right. What are 2 ways to increase the choking impedance of a ferrite choke? More turns, more beads. Now, you're the first person that I heard say it. All right, there you go. That's a Walmart RFI kit. All right, the questions are going to get harder now because the prizes are getting bigger.
More beats, more turns.
Name 4 ferrite mix numbers used by hands to suppress RFI.
31, 43, 73, and 77.
All right. Yeah, the guys in the front row have an
Yeah, they
advantage.
sit in the front row.
So, you got a 31.
Bingo.
Well, that's the most popular one, right? Okay, next one. What is one of the best kept secrets in ham radio? Joseph. Congratulations. What's the answer to this one? The answer is they taste funny. Give it to somebody. And the last question, of course, is when you're having problems, who do you call? All right. That's my contact information. You can go to the website. This presentation is on the website in all different types of formats. And you're welcome to look at that. And there's a good tutorial on all the things that we've been talking about, with specific examples of what to do for all that. Thank you.
Oh, what a great presentation. Hang on a second. Don't leave yet. Don't leave yet. Not you, man. Thank you again for that presentation. One more round of applause. One more thing.
I have some cheat sheets that you can take with you, which basically
He's got some cheat sheets, so there's some flyers here to look at. So two more things. One, if anybody ordered a polo shirt and hasn't gotten a replacement one from me, come see me. I have some with pockets now. So I think, Charlie, I've got one for you up here, I think. And Some others, yeah, I've got cleanse. So if you ordered a polo shirt and it didn't come with a pocket, come see me. I probably have one. Joe, you too. And the second thing is, along those same lines, if you're interested in ordering them, please send an email to board or to me, k6jpe@arl.net, and let me know so I can get you on the list for the next order. We need 20 in order to order, so let me know, and then I'll let everybody know when I have enough. Oh yeah, and go see Charlie's video back there for a demonstration of the radio for the deals. So, and buy stuff. John does not want to take this stuff off the goodie table home, so somebody else take it home. It needs a new garage to live in. Thank you everybody for coming. See you next month. And we're having cake, so come over here and have cake.
I was hoping to have